So imagine handing a construction crew just a napkin sketch,
Yeah.
and in, I don't know, like 3 seconds flat, they build you a massive 3-story house.
Right, which sounds amazing.
It sounds like a total miracle, right?
Yeah.
Until you walk inside and you realize that because they moved at light speed, they routed the plumbing directly through the electrical panel.
Oh, yeah. Not ideal.
Right. The faster they built it, the faster the whole structure just rotted from the inside out.
Yeah.
So today we are looking at a presentation deck titled Blueprints and Automated Minds Bridging Software Design and AI. And it tackles that exact paradox, but in the world of software engineering.
It's an incredibly timely set of sources. I mean, the deck breaks down everything from, the classic design patterns we've relied on for decades to this really cutting-edge AI architecture called the Design Pattern Summarizer, or DPS.
Okay, let's unpack this, because our mission for this deep dive is to figure out why, in a world where AI can basically just instantly spit out thousands of lines of code, why these old school, rigid architectural blueprints drawn up by humans are actually becoming more critical than ever before.
Yeah, what's fascinating here is the context of these sources. We have officially reached a point where the physical typing of code it's no longer the bottleneck in software development.
Right.
Large language models have largely solved the syntax problem.
It just generate it.
Exactly. But by solving that, they've exposed this much deeper, much more insidious structural problem that engineering teams are really just starting to wake up to.
Well, okay, I want to push back on that right out of the gate, though.
Sure.
Because if I'm managing a development team or I'm a startup trying to get a product to market, speed is the holy grail.
Oh, absolutely.
So if an AI can generate a working feature in 3 seconds, why is hyperspeed suddenly a bad thing? Like, why are we telling developers to slow down, dust off old blueprints, and obsess over architectural rules?
Well, it's because of a mechanism the researchers refer to as software aging.
Software aging.
Right, which is being fundamentally warped by what they call the AI accelerator.
Okay.
So software aging isn't about code literally expiring like milk.
Right.
It is about architectural drift. It has the gradual degradation of a system's structural integrity over time as new features are bolted on.
Right, just stuff getting messy.
Exactly. When humans write code, this decay happens relatively slowly. But when you introduce AI-assisted syntax generation, you don't just speed up production, you introduce the AI accelerator.
So it's essentially technical debt on steroids.
Worse, it's automated architectural collapse.
Wow.
Because AI doesn't inherently understand the long-term, multi-year vision of your software system. An LLM operates by finding the most statistically probable way to complete the immediate localized prompt you just gave it.
Just whatever's right in front of it.
Right. So if the fastest way to make a button work is to, bypass your carefully designed data layers and just write a direct, hard-coded database query right into the user interface, the AI will just do it.
Taking the path of least resistance.
Yeah.
It just wants the green check mark for the current task, like task done, move on.
Precisely. The research shows that without high-level architectural constraints, this AI acceleration turns clean blueprints into just bloated anti-patterns.
Right.
You end up with this messy web of hyper-coupled dependencies where, changing a single variable on a login screen breaks the payment processing module.
Wow. Yeah.
The machine just patches and hacks its way to immediate success, totally blind to the structural rot it's leaving behind.
Which means writing code isn't the hard part anymore.
No, not at all.
Maintaining a comprehensible architecture that an AI won't accidentally destroy is the hard part.
That is the new reality.
Wow.
And it is why developers have to master the specific structural defense mechanisms that keep systems modular and decoupled.
Okay, so let's get into those defense mechanisms then.
Sure.
The resilient blueprints. The sources dive pretty deep into the coupling spectrum, from like loose temporary dependencies all the way up to really rigid inheritance.
Right.
But since our audience already knows the basics of object-oriented programming, let's bypass the beginner definitions and look at why AI specifically breaks certain paradigms.
I think that's the critical distinction. If we look at the rigid end of the spectrum, inheritance, we find the AI's biggest trap.
Okay.
Inheritance forces and is a relationship. It is a strict vertical hierarchy.
Right.
So if you have a deep inheritance tree, any change at the top cascades all the way down, and any new requirement often demands a highly specific new subclass.
And the research highlights how quickly that turns into a nightmare
Yeah.
when an AI gets involved. Because if I think about inheritance, it's like hardwiring your entire house to only accept one very specific brand of refrigerator.
Yeah.
And the moment you want to switch to a different appliance, you basically have to tear down the drywall and rewrite the house's electrical grid.
That's a perfect way to visualize it. When an AI hits an inheritance tree and it receives a prompt for a new feature that doesn't perfectly fit that rigid structure, the AI doesn't carefully refactor the entire hierarchy.
Because it's lazy or it just...
It takes too much compute and context.
Right, okay.
Instead, it just duplicates massive chunks of code, creating parallel, messy subclasses. It just tapes new branches onto the tree until the whole thing collapses under its own weight.
So the structural blueprint that defends against this AI behavior is composition. Like the sources say, delegate, do not multiply.
Exactly. Composition changes the fundamental relationship to has a dynamic.
Right.
Instead of building an infinite brittle tree of highly specific classes, you extract behaviors into distinct interchangeable interfaces.
So it's moving away from the hardwired house and moving toward like a modular rig.
Yeah.
Like standardized shipping containers, I guess. Like a cargo ship doesn't care if a container holds electronics or fruit, right?
No, it doesn't.
It just knows how to lock the corners of the box. You just plug and play.
And that plug and play modularity is exactly what an AI needs to operate safely.
Really?
Yeah, because when you use composition, you isolate behaviors. You give the AI a contained sandbox to generate syntax for one specific module without risking the integrity of the entire system.
I see.
Which leads us directly into the ultimate defensive structures detailed in the sources, which are the solid principles.
Right, the solid principles. These are the rules that keep the machine from turning our architecture into spaghetti.
Exactly.
So let's look at the single responsibility principle, or SRP, and the open closed principle, OCP. Because I want to build on your sandbox idea here.
Go for it.
SRP dictates that a class should have one and only one reason to change.
Right, so think about the blast radius of a bad AI hallucination.
Exactly. If I have a module that handles both my user authentication and my database routing, and I ask an AI to update the login screen, a hallucination might rewrite my database logic by accident.
Yeah, and the blast radius is massive.
Huge.
Yeah.
But if I enforce SRP, it's like building watertight compartments on a submarine.
Oh, I like that.
Yeah, so if the AI hallucinates and floods the login compartment, the database compartment is sealed off, so the submarine doesn't sink.
That isolation is key. And it pairs directly with the open-closed principle.
Right.
Software entities should be open for extension, but closed for modification.
Meaning you can add new features without ever touching the core tested code that already works.
Yes,
It's like a food truck.
a food truck.
Yeah, if I want to start selling tacos instead of just burgers, I don't rebuild the entire engine of the truck.
Right.
I just add a new menu board and maybe a different grill insert. But the truck itself remains completely untouched.
The AI can generate the code for that new taco module, basically extending the system without being given permission to modify the core truck engine.
Yeah. This brings us to a mechanism that this sources emphasize really heavily, which is dependency inversion.
Oh, I love this one because the research frames it as the flip.
The flip, yeah.
Because in a traditional fragile architecture, your highly important business logic rests entirely on the shoulders of low-level details, like a specific database connection.
Right. It's a top-down dependency. The high-level policy is hostage to the low-level mechanism.
Yeah.
If the low-level database cracks, or if an AI tries to optimize it and breaks it, everything resting above it just shatters.
So you flip it, you invert the dependency.
Yeah.
Instead of the high-level logic being hardwired to the database, you introduce an abstraction layer between them.
Exactly.
It's literally like an electrical outlet.
Go on.
So if I have a lamp lit, I don't want to hardwire the lamp's power cord directly into the copper wire inside my wall.
No, that would be terrible.
Right, because if the lamp breaks, I have to call an electrician. The copper wire is the low-level detail. Instead, we install a standard electrical outlet. That outlet is the abstraction.
So now the wiring in the wall points to the outlet, and my lamp points to the outlet.
The details depend on the abstraction.
Right. And if I want to swap my lamp for a television, the wall wiring doesn't care. It's completely protected.
Yeah.
In software, if I tell an AI to swap out a MySQL database for a cloud storage solution, the AI can't accidentally break my core business logic because the business logic is only talking to the abstract outlet.
That is brilliant systems thinking. And it's important to note where this comes from. The sources draw a direct line back to Christopher Alexander, who was an actual building architect.
Oh, wow.
Yeah, he realized that physical spaces have recurring timeless patterns that solve specific human problems. And the famous Gang of Four software engineers took Alexander's concepts and adapted them into the foundational design patterns for object-oriented programming.
Right. They essentially codified the language of complexity.
They did, but that language was built for humans. It relies on a human developer looking at a massive code base and intuitively understanding, this is a dependency inversion, this is an abstract factory pattern,
Yeah.
which brings up the crucial pivot of this entire research.
Well, and this is where I have to throw a flag on the play,
Okay.
because we've talked about how these blueprints constrain the AI.
Mm.
But large language models are fundamentally just massive statistical prediction engines.
True.
They're trained to predict the next token, the next word.
Right.
So how can a machine actually read a structural blueprint? I mean, isn't it just scanning millions of characters of text like a giant autocomplete?
Right.
It doesn't actually know what an electrical outlet or a submarine compartment is?
If you treat the AI as a simple text predictor,
Yeah.
you will inevitably run into the architectural drift we talked about.
Right.
Reading code line by line is like trying to understand the plot of a novel by reading a dictionary.
Oh, I see.
You get the words, but you miss the narrative. And that is exactly what the researchers solved with the DPS architecture.
The design pattern summarizer.
Right, developed out of Ada University and the University of Melbourne.
Okay.
The DPS architecture completely abandons the idea of reading code as linear text. It introduces a pipeline specifically designed to parse structural intent.
Okay.
It reads the code exactly the way a compiler does, but it uses that view to feed the AI.
Well, here's where it gets really interesting, because the researchers break this pipeline down into 3 highly specific mechanisms.
Yeah, they do.
Step 1 is the Java parser, which converts the raw code into an abstract syntax tree, or an AST.
This is the core of the breakthrough. An AST doesn't look at syntax, it looks at hierarchy.
Oh, okay.
It takes a flat file of text and translates it into a 3-dimensional mathematical graph.
Wow.
So the root of the tree branches off into nodes representing statements, expressions, loops, and variables.
So it's graphing the relationships. It stops seeing words and starts seeing load-bearing walls and dependencies.
Exactly. By converting the code into an AST, the machine escapes the trap of linear text prediction. It can visually see, mathematically speaking, that Class A inherits from Class B, but Class C is injected as a dependency. It maps the physics of the software.
Which sets up step 2, right? Feature extraction.
Yes.
Because once the code is mapped as this 3D graph, the DPS hunts for exactly 20 structural and object-oriented features.
It is actively scanning the AST for the signatures of the human defense mechanisms we just discussed.
But how does an algorithm actually spot something abstract, like encapsulation, inside a mathematical tree? I mean, how does it know?
It looks for specific node boundaries.
Yeah.
If the algorithm sees a cluster of private field nodes that can only be accessed through public getter and setter nodes, and those references do not cross into other tree branches,
Right.
the machine flags that entire subtree as highly encapsulated.
Oh, wow.
It is measuring the coupling distance between nodes. It maps the context at both micro-method level and the macro class level.
So it is identifying the watertight compartments.
Exactly.
And once it maps those 20 features, it moves to step 3, which is simple NLG, or natural language generation.
This is where it translates the math back into English.
Okay.
The system takes all of that deeply parsed structural intent, the knowledge that this node is an abstraction layer and that node is an encapsulated database module,
Yeah.
and it generates a human-readable summary. So it doesn't just tell the developer what the code says, it explains what the architecture is doing.
Okay, so the theory is incredibly sound. It takes code, it turns it into a mathematical tree, it measures the structural physics and translates it back.
Right.
But does it actually hold up in production? Like, does this pipeline understand context better than a senior developer who has been working in the code base for years?
Well, the researchers didn't just theorize, they ran empirical evaluations across both educational repositories and complex real-world production systems.
Right.
And they used a gauntlet of statistical metrics to prove it.
Yeah, they use BLU4, NIST, Rugel, and Frugal Score. Let's break down what these are actually measuring, because it's not just about grammar, right?
Right, exactly. So BLEU4 and Rugel are evaluation metrics that look at nanogram overlaps.
Okay.
Essentially, they check if the machine's generated summary uses the exact same foundational multi-word phrases and concepts as a high-quality summary written by a senior human developer.
Got it.
They measure precision and recall. And then NIST weights the rarer, more highly specific architectural terms to ensure that AI isn't just generating generic fluff.
And Frugal Score.
Frugal Score validates the semantic meaning, ensuring that AI summary genuinely means the same thing as the human A summary, but it does so efficiently without burning massive amounts of computational power.
Right.
And across all these statistical checks, the alignment between the DPS system and ground truth human intent was just incredibly tight.
But statistics only tell half the story. The real jaw dropper is the expert survey,
Oh, yeah.
because they put the machine head to head with human experts to evaluate a metric called context captured.
They asked human evaluators to score how well the summaries captured the true architectural context of the system on a scale of 1 to 6.
And the human-generated summaries, written by actual developers, scored a 4.0 out of 6.
Which is a passing grade, but it shows that humans naturally miss things.
Right.
We suffer from cognitive load. When a human looks at thousands of files, they miss the forest for the trees.
But the DPS system S's summaries scored a 5.5 out of 6 for context captured.
It's amazing.
The machine was objectively better at understanding and summarizing the structural reality of the code base than the humans who built it.
Because the machine doesn't suffer from cognitive fatigue.
Yeah.
Once it builds that abstract syntax tree, it sees the entire forest instantly.
Right.
It maps every dependency perfectly, and crucially, it does it in a fraction of the time. The research notes that using this AI summarization dropped the time required for developers to comprehend a new code base from several minutes per module down to mere seconds.
Wow. So what does this all mean? I mean, if you're a software engineer or a technical lead listening to this right now, what is the core takeaway? Because it feels like the ground is just shifting beneath our feet.
The core takeaway is that the fundamental role of the human developer is changing permanently.
Okay.
We are transitioning from being syntax writers to being structural editors.
Textual editors.
Yeah.
Yeah.
The days of manually typing out loops and boilerplate are over. The AI can write the syntax faster and better than we can.
So our job is to basically build the sandbox. We have to become the architects who hold the blueprints.
Yes, the classic design patterns, the solid principles, the gang of four structures, they are no longer just tools for humans to communicate with other humans.
Right.
They are the scaffolding we must use to constrain and guide automated minds.
I see.
By anchoring our code in these proven resilient blueprints, we give the AI the context it needs to act as a collaborative engine rather than, an accelerator of decay.
Right. So structure is the new language we use to speak to the machine. We aren't really teaching them to code anymore. We are teaching them to build.
But they can only build a resilient structure if we provide a resilient blueprint.
Yeah.
If we abandon our architectural disciplines just because the AI is fast up, we will bury ourselves in technical debt faster than ever before.
It's a fascinating paradox.
Yeah.
We started by picturing an AI as a chaotic construction crew,
Yeah.
Threatening to leave us with a tangled mess of red scribbles.
Right.
But by enforcing the oldest, most rigid human design rules, by forcing the machine to respect composition and dependency inversion, we actually unlock its true potential.
Exactly.
We give it the structural graph it needs to understand our intent perfectly.
It really proves that human architectural intuition combined with machine speed is far more powerful than either one alone.
Which leaves me with one final thought to mull over.
Oh, yeah.
Yeah. We've established that by mapping our human blueprints, an AI like the DPS system can understand our structural intent better than we can. I mean, scoring a 5.5 compared to our 4.0. True. But right now, the AI is reading our blueprints. It's confined to Christopher Alexander's concepts and the patterns we invented to handle human cognitive limits. What happens a few years from now when the AI realizes it doesn't have those limits? When it starts inventing entirely new multidimensional structural paradigms to optimize its own syntax generation.
Oh, wow.
I mean, if the machines move past the gang of four and start drawing their own blueprints, will human structural editors even be able to read the architecture the AI builds for us?
That is the ultimate frontier.
Keep questioning the structure of things. Catch you on the next deep dive.